the Pythagorean theorem states that if you have a right triangle with the two shorter sides length A and B, and the long side, the hypotenuse length C, then A squared plus B squared equals C squared. So you've known this relationship for a long time, but you may have never seen a proof of it, and I'm going to show you a reasonably understandable proof right now. And I can do that with the aid of the technology. I'm going to make 4 copies of this kind of generic triangle I have in the statement of the theorem. So I'm going to make 4 copies of that very quickly, much quicker than I could do by hand. And I'm going to rearrange them to form a big square. So does everybody see the big square then that I've created? Okay. Now, there's also a little square within the big square. So the big square has sides of length A plus B. Right? But there's also a little square. Now, wait a minute. I mean, it looks like a square inside, right? The square with sides of length C. Does everybody see it? But how do we know for sure that this is a right angle right here? And, of course, the others as well. How do we know? But if one of them is a right angle, they're all a right angle. How do we know that they're all right angles? Well, it comes from the fact that that triangle, it's a right triangle, and in any triangle, the sum of the angles is what? 180 degrees. So since we know that this angle here, for instance, is 90 degrees, then these 2 angles left over have to add up to be 90 degrees. But this angle here matches this angle here. So these guys together make 90 degrees, which means there's 90 degrees left over. So it really is a square on the inside. It's not a visual trick or anything. So, okay, right about now you're thinking, well, where does the Pythagorean theorem come into play? A squared plus B squared equals C squared. We're going to find the area of the big square in 2 different ways, and the Pythagorean theorem is just going to fall out of that with we hardly have to try. It'll just appear. A little bit of algebra, a little bit of algebraic trickery. Okay, so looking at the big square, it has sides of length A plus B. Well, how do you find the area of a square? So the area of the big square with sides of length A plus B. Well, couldn't you just take A plus B times itself? A square is a rectangle, right? So you take the length times the width, which are both the same. They're both A plus B here. Wouldn't that be a way to represent it? But what's a simpler way to write A plus B times A plus B?
A plus B squared.
A plus B squared. Okay, but there's another way to express the area. We've got 4 copies of the same triangle, right? Around kind of the perimeter. So we've got 4 copies of this triangle right here, right? And it has this area that I'm kind of shading in right now. 4 copies of this triangle, 4 copies of this same area all the way around. So couldn't another way to find the area then of the big square, couldn't we add all of the areas of these 4 triangles together and the area of the little square? Wouldn't that also be a way to get the area of the big square? Does everybody see what I'm saying? Okay, so what's the area of the triangle? Focus on this guy. What's the area of the triangle with leg A, leg B? Any triangle, so it doesn't have to be a right triangle. Say it has height H and base length B, then the area is 1/2 base times height, right? But in this case, for this right triangle, the base you could think of as A, or you could think, if you look at this version of the right triangle over here, you could think of this base as B if you like. But I'm going to go in alphabetical order. So 1/2 A times B in this case, right? but there's 4 copies of it. So if you go 4 times 1/2 A times B, that's going to be the area from the 4 triangles. They're all going to have the same area, so just multiply by 4. But then you also need the area of the inner square, which is going to be what? Since it has sides of length C, to get the area of the to add together to get the area of the entire big square. Well, what's the area of a square with a side of length C? C times C. So plus C squared. Does that make sense to you? You believe that? So you add all of the areas of the triangles together plus the area of the square together, you should get the area of the big square. So that's just another way to express it. But look, on the right side, if you multiply 4 times 1/2, what do you get?
2.
So you get 2ab plus c squared. On the left side, there's a formula for multiplying out a plus b quantities squared. Anybody remember what it is? So kind of separate that. Remember, you square the first guy, which is a. You take the first guy a times the second guy b, double it, and add that in. And then you add in the last guy squared. Remember that formula? Now, we're just about there. All you have to do is realize you've got a plus 2ab on this side and a plus 2ab on this side, and just subtract it out from both sides. It'll disappear. And then if you do that, what's left? A squared plus b squared equals c squared. So that's it. That's the proof. Done.